Welcome everybody to the start of the Build It track on Saturday of the last ShmooCon. We're going to miss you all, so thank you for coming all the times that you have over the last 20 years. And I want to introduce Michael Osman, who has been here many times with many great hardware hacks. And today, building and hacking USB with FPGAs.
Thank you, John. Thank you, ShmooCon. Thank you, everybody. It's great to see your beautiful masked faces. Before I start, I just want to say it's a little hard for me to be here today for multiple reasons. One of those is that my brother and his family live in LA, and their house was destroyed this week. It gets completely burned to the ground, and they have nothing left. I'm truly excited to be here talking to you about these things today, but it's a little hard to just kind of make that switch. But I do want to just say, if it is in your power to lend a hand to the thousands of families that are in the predicament that they are in, I hope you'll do so. But I am here today to talk about open source tools for building and hacking USB with FPGAs. And in case I don't mention it later, everything in this talk, every hardware project is open source hardware that I talk about today. Every software project is open source software. 10 years ago, on this very stage, Dominic Spill and Jared Boone and I were here talking about other open source USB tools. And one of those was Daisho, which is this board. What I'm showing you now is the Daisho main board. And Daisho had this the big square chip in the middle is an FPGA, a field-programmable gate array, which is basically just a big mess of logic gates that could be configured in different ways. So it can, I guess we're going to continue to have fun with the projector today. It'll probably come back in a moment. There we go. It can be configured on the fly to basically be a different set of hardware. So if you wanted to make a custom digital ASIC, a chip, you might prototype it on an FPGA, and that's maybe the most traditional use of an FPGA. But for us, we really want to continually be able to reconfigure it and do different things every time we use the FPGA. And the chip that's below that, at the bottom, toward the bottom, is a physical layer transceiver, or a PHY chip, for super speed USB. And so the architecture of Daisho actually had two boards. I showed you the main board, but there was a front end module that would plug into the other side of it. And for USB, in the case of USB, we had a front end module that had two more of those super speed USB transceivers. And so we had this architecture where there's an FPGA in the middle, and then three PHY chips, and then three super speed USB connections. And then on the right-hand side, you can see a target device would connect to a target host through the Daisho, and then we could monitor that or do meddler in the middle things. And we demonstrated this at ShmooCon 10 years ago, and we just barely had it working to where we actually got the super speed USB link up, and that was it. And that's the last you ever heard about Daisho. I want to clarify some things, just refresh your memory about USB speeds, because I was talking about Daisho being super speed. USB comes in a bunch of different flavors, different speeds. Low speed is 1.5 megabits per second. Full speed is 12 megabits per second. Now, low speed, you probably don't have very many low speed devices unless they were made in the 20th century. Or maybe if you have a mouse, a simple mouse is about the only thing you're likely to have that's a recent low speed device. Most USB devices today are full speed. Somebody making a new USB device today, unless they have a particular reason to use a different speed, they're probably going to make it full speed. If you buy a microcontroller that has a built-in USB device controller, most of those are full speed devices. But a few are high speed. And high speed devices are things like like this HackRF1, we need that extra speed, 480 megabits per second, to transfer the, the radio data from, at a high rate. So we need that. And then super speed is 5 gigabits per second and up. There are different flavors of super speed, and they keep changing the names of them, and it's very confusing, but basically super speed, or super speed plus, or whatever they're calling it now, is 5 gigabits per second or 10 gigabits per second or higher. And actually, I'm not going to be talking about super speed much today, because USB 2.0 is the standard that defines low speed, full speed, and high speed. And it is a 25-year-old standard, but it is the current standard. It is the current standard for low speed, full speed, and high speed, which, as I said, is most USB devices. There's a USB 3.x standard for super speed, and that's what we were trying to work with the Daisho project, which was pretty new back during the Daisho project. And now there's USB 4, which is like this convergence of Thunderbolt and USB over the same cable. And Thunderbolt itself was already multiplexed DisplayPort and PCI Express. So now you have PCI Express and DisplayPort and USB and SuperSpeed USB and USB 2.0 and even other things that are all multiplexed over the same cable. And a USB 4 cable is really like a bundle of cables, and one of those cables is USB 2.0. USB 2.0 is the most universal of all of the USB interfaces because everything is meant to be backwards compatible with it. And like I said, that was the last you probably ever heard of Daisho in 2015 at ShmooCon. Our funding ran out. Daisho was funded by the Cyber Fast Track program, thank you, Mudge. And it was a really cool research project, and it was a cool proof of concept. But when our funding ran out, we realized we were a long way from actually having like a marketable product. It was an expensive board to make. It would have been expensive to like manufacture and sell, and there was a lot of software work to go from proof of concept to like something that was be useful to carry in your bag. So we abandoned the project at that time. After Daisho, at Great Scott Gadgets, I'm the founder and CTO of Great Scott Gadgets. We make things like HackRF1 and other things that I'm talking about today. But after Daisho, Dominic and Taylor and I at Great Scott Gadgets sat down and started brainstorming, what are we going to work on next? And one of the concepts we had was this USB star concept. We said, what if we took the Daisho concept and stripped it down to a single board instead of this pair of boards, and we made it USB 2.0, and it was just an FPGA and 3 USB 2.0 PHYs. It would be like a much more affordable, much more achievable goal than we had with the super speed Daisho arrangement. And Daisho was actually trying to do more than just USB. We had front-end modules for other things like HDMI and gigabit Ethernet and stuff. And we scaled that concept down. But we also had this concept to do GreatFET. And GreatFET was inspired by Travis Goodspeed's GoodFET and Facedancer project. And we wanted to build a better GoodFET and a better Facedancer. And it was microcontroller based and had 2 USB ports. So it could do all of the things that GoodFET and Facedancer did and more, including a lot of useful USB stuff. And so we decided to focus on GreatFET at the time and abandon the USB star concept because it just made more sense for us. Part of the reason is that Dominic and I didn't really know what we were doing with FPGAs. And the friends that we hired to help us with that during the Daisho project, like Jared and Marshall, we couldn't afford to pay them anymore because we didn't have the external funding. So, we took the more achievable goal of GreatFET, and we worked on GreatFET for a few years. And GreatFET is still a thing, but after a few years, Kate Temkin was working for us, and she did a lot of work on GreatFET and Facedancer. And one day she just kind of turned up at the lab with this design and said, "Hey, look, I made a USB sniffer." She'd been trying to make a USB sniffer on top of GreatFET. It was an add-on board, which we call a neighbor for GreatFET, and you could do passive USB monitoring with your GradeFET and this add-on board. And it was pretty cool. But like she had been running into sort of like frustrations with that architecture and realized, well, maybe it would be better if we just kind of built something new from the ground up. And so she designed this thing. And I looked at it, and this was like late 2019. I looked at it and I was like, wow, you made USB Star. And she was like, what are you talking about? And she just independently came up with this. And this is the design that ultimately became Cynthion, which we started shipping actually just in the last year. And yay, Cynthion. So Cynthion is a USB test instrument. It's a USB multi-tool. And the architecture, if my slides come back, there we go. Okay, let me show you just what it looks like inside the enclosure. There's this FPGA in the middle, and 3 USB PHYs, and actually 4 USB ports. And the reason there are 4 ports and not 3 is because on the right-hand side, you can see there's a target Type A port and a target Type C port. And target C and target A are wired directly together and share a transceiver, a PHY chip. So you can do pass-through, and the Cynthion can passively monitor that pass-through USB connection. It's all USB 2.0. Very similar architecture to Daisho, but USB 2.0, not super speed. So Cynthion tries to be 3 things. It's a low-cost, high-speed USB analyzer, it's a USB hacking multi-tool, and it's a general-purpose USB and FPGA development platform. Now, along with Cynthion, Kate started this Luna project, which is a USB gateware library that's built with Amaranth HDL. And originally Luna was intended to be like an acronym, and we were trying to figure out what it would stand for, like lightweight USB something, something, and we never figured out what the something, something meant, so we started calling it LAX, a universal naming acronym. And it's used in various projects, not just our own Cynthion, but some other projects that we have going, and some external projects that are not at Gray Sky Gadgets, like OrbTrace, which is an ARM debugger, and Tiliqua, which is a very soon-to-be-released audio multi-tool in a Eurorack form factor. It's really cool. It's FPGA-based, and these things have USB connectivity provided by Luna. Built in so we can build USB device controllers in the FPGA with Luna. So you might have noticed that first screenshot of Kate's design, the thing that ultimately became Cynthion, was originally labeled Luna. And you may have seen reference to this elsewhere in the past, that there was this board called Luna. Doesn't exist anymore. Well, it kind of does. We renamed it to Cynthion. So we had these 2 things called Luna. We had this gateware library, and we had this piece of hardware, and they were both called Luna, and it was very, very confusing. We had many conversations, like internally at Gray Sky Gadgets, where somebody would say something about Luna, and then somebody else would say, do you mean Luna, the gateware library, or do you mean Luna, the hardware? And so we were like, this is a problem. We need to rename one of these. So we renamed the hardware to Cynthion, which is a much more unique name and trademarkable. And in fact, as of this week, is a registered trademark. Yay. Thank you, Elizabeth. Luna, the gateware library, is still called Luna. And Luna, the gateware library, is built with Amaranth HDL, which is this amazing hardware description language. If you have ever done any work with FPGAs before, you've probably used more traditional hardware description languages like Verilog or VHDL, and I'm sorry, but we are now using Amaranth HDL, which is a Python-based hardware description language. So we write our gateware for the FPGA in Python. We run a Python program, it generates a bit stream for the FPGA and loads it onto the Cynthion, and it just works. And it's incredibly fast and really a joy to work with, in large part not just because of Amaranth HDL, which is developed primarily by Whitecork, but also because of this whole ecosystem of open source FPGA tools. In particular, we use Yosis for synthesis and NextPNR for the place and route on the FPGA, and Project Trellis, which documented the ECP5 FPGA that we're using in Cynthion. And because of all these projects, it just works. Literally, you don't even have to know much about any of these things. You just run a Python program, and it just builds the bitstream for you, and in like seconds, which is amazing. Like we do a whole USB device controller and more in like 30 seconds, and it just synthesizes and loads it onto the device, and everything just works. I love it. So I want to show you Packetry, which is our USB analysis software. So this is a screenshot of Packetry, and I'm sorry that my font is going to be a little bit hard for some of you to read. You're just going to have to trust me on some of the things that I say here. But Packetry is USB analysis software. You know, it's like a packet analysis that lets you, when you do monitoring of USB with Cynthion, you can analyze the traffic with Packetry. And you're probably looking at this and thinking, they could have used Wireshark. So why not use Wireshark? And to show that, I think the best thing to do is to give you a demo. So I'm going to show you Packetry. And I had to change my screen resolution to try to make the projector behave better, but it's not. So I'm going to go back to the other resolution that's going to make this more visible to you, I think, because we're going to just keep having the projector turn off from time to time, and we're just dealing with that. And hopefully it'll come back in a moment. There it is. So now that's probably a little bit more visible to you. So let me just show you. This is something from my setup. I'm going to restart a capture here with Cynthion and just plug in a HackRF. So I've just plugged in HackRF1, and we're seeing the host operating system having enumerated this HackRF device. And you can see, for example, like the operating system is asking the device, what are you called? And the device replies, I'm called HackRF1. And you can see that this transaction, or like this transfer of this device name is made up of these 4 transactions, and these 4 transactions are made up of these multiple USB packets. And this is a big part of why we decided to build our own tool in Rust instead of using Wireshark, is because we wanted to display these things in hierarchical mode. And my screen's a little messed up from having changed my resolution so many times. There we go. There's a device panel over here that summarizes information that it automatically figured out by looking at, by seeing these device descriptors and like string descriptors go by and stuff. Let me show you the same thing in Wireshark. So if I look in Wireshark and I just stop this and start a new capture, I'm using the USB Mon facility of Linux here to capture with Wireshark, which is, if you've ever done USB with Wireshark before, that's probably what you did, something like that. So I plug in the HackRF, and I'm going to stop this capture now, and you can see some of the same sorts of things, like string descriptors. Here's a response of a string descriptor that is, oh look, it's HackRF1. Very similar stuff that I can see with Wireshark. But guess what? Wireshark shows me a request and a response. And these are USB herbs. What's a USB herb? Well, it's a USB request block. And if you read all 650 pages of the USB 2.0 standard, you will find 0 references to herbs. It is not really a USB thing. Where will you find documentation about what an herb is? Look in the Linux kernel source or the Linux kernel documentation, because and there are similar data structures in other host operating systems. What you're seeing here with Wireshark and USB Mon is the Linux kernel's view of USB. Your host computer has a USB host controller, which is like a separate chip that handles the USB connection on behalf of the CPU. And so you're seeing the operating system asking the host controller to do USB stuff for it. You're not actually seeing the USB stuff. The USB stuff that goes over the wire looks quite different because all I'm seeing here is a request and a response. But when I looked in Packetry, look, I saw this request and I saw that was made up of a transaction, that was made up of packets. And I see the individual packets that went over the wire. And if something went wrong here, I would only be able to see it in these packets over the wire, and I might not see it at all show up in Wireshark with USB-Mon. So, okay, this isn't really an issue between Wireshark and Packetry. Really what we're seeing here is an issue with USB-Mon versus sniffing on the bus with the Cynthion or some other hardware USB analyzer. So one thing we can do is save this capture with, from Packetry. So I'll just call it like hackrf enumeration.pcap. I can save this as a pcap file from Packetry and actually open it up in Wireshark. Let's take a look at that, what that looks like. I named it the same thing as I had before. So I open it up and I see tons of these startup frame packets. And I'm scrolling through all these tiny startup frame packets. Scrolling and scrolling. Okay, so in Packetry, those startup frame packets did in fact exist, but Packetry hides them under this SOF group. And you can dig into them if you want, but most of the time you probably don't. On rare occasions, they're useful, but most of the time they're not. Now in Wireshark, probably the way you want to deal with that is to do a filter. We can apply as a filter, not SOF packets. And now we're starting to get some useful things in Wireshark. You can see those individual packets. However, I find them harder to make sense of because they are not presented in the hierarchical form that they are in Packetry. So this is really, there are a couple of different issues here. One is, where do we sniff? Do we sniff at the host CPU, or do we sniff on the wire? But another issue is, how do we present this data to the user? These packets are much easier to understand if you can present them in a hierarchical way. And there's another reason why things might be a little bit harder to deal with in Wireshark. I want to show you, if I do a capture with Cynthion, and let me make sure it's working by resetting my hackrf. There we go. We're seeing, well, I'm seeing, you'll see in a moment. We're seeing these packets come in with hackrf. And then if I actually run some hackrf commands, like hackrf info, I can actually start to see some interesting traffic go by. And if I do a hackrf transfer, which like actually transfers a bunch of radio data, like now I'm getting some real throughput, right? And look at the packet count at the very bottom of my screen. I'm already up over 1 million packets in Wireshark in just like a second, right? I'm already over 2 million packets now. And I'm not even using hackrf at its maximum sample rate. I'm using it at its default sample rate. And the number of packets, and a big part of this is those tiny little startup frame packets. The number of packets that you get on a USB wire is incredible. Like the rate is unbelievable. I'm going to stop this at 6 million or so. And Packetry performs just fine. And I can see all the, these bulk transfers and all the data being transferred. And if I save this, hackrf transfer.pcap, if I save this, if I reopen it in Packetry, I think you'll see at the bottom of the screen there's that progress bar. Did you see that? It only lasted for a second or two, right? Now, if I open that same file in Wireshark, let's see what happens. If some of you are groaning already. You know what's coming because you've worked with Wireshark before. Now, don't do it. Here we go. Open hackrf transfer.pcap. Okay, now there's a progress bar at the bottom of the screen. There's a progress bar. Do you see that little blue sliver? That's the progress bar of opening this file of 6 million packets. And it's just not the performance that we need, especially to do real-time monitoring and display, right? Wireshark is fantastic software. I highly recommend it. It is a wonderful tool, but it's not designed for USB. So we decided to build Packetry from scratch. Mostly Martin, thank you Martin, has built Packetry from scratch in Rust. And I'm just going to stop this. There we go. OK, file loading was canceled. Oh, another thing is, not only did Packetry load the file quicker, but even when it was not finished loading, it let you interact and view, you interact with and view the packets that it had loaded already. So Wireshark, you don't actually see that until you've canceled or finished loading. So I'm going to go back to my slides here. Here's a screenshot of Wireshark, and here's a screenshot of, I have changed my screen resolution, and things are not real happy. That's better. OK, so here's a kind of future screenshot of Packetry. One thing you might like is dark mode, which actually works now. But another thing you might like is these hierarchies can be a little bit hard to visualize. We have all these lines and curves kind of connecting things together. They're getting better. They're getting smoother and more connected and better. And one thing that's really cool is that in Packetry, we have a hierarchical view. We also have a transaction view. And if you want, you can even look at a packet view. And it kind of looks similar to when we opened that capture in Wireshark, where, oh, these start of frame packets. But occasionally, packet view is handy because it's strictly chronological, whereas the hierarchical view is not strictly chronological because it's grouped these transactions together, it's grouped these transfers together, which are multiple transactions. But over the wire, especially if you have multiple devices on the same bus, you might have a transaction from one device interleaved with a transaction of another device, and it gets really hard to really understand, like, not only what's happening at the higher layers of the protocol, but also what's happening like over the wire if there's some kind of physical layer problem. So we have this new thing that's coming out. It's going to be a fourth view, and there's a pull request already, and that Martin has been working really hard on, which is interleaved hierarchical mode, which is amazing because it gives you both the hierarchy and strict chronology at once. And it's kind of hard to visualize until you actually see it, but it's really cool. So I want to talk next about Facedancer. Facedancer was originally a hardware platform created by Travis Goodspeed and Associated Software, and it was a variant of the GoodFET project. So his original GoodFET looked a lot like the left-hand half of this board, and then he added on to it to create the Facedancer board, which was it basically added a USB device controller onto it that could be controlled from the other USB device. So you have two USB devices back to back. One of them connects to your host computer, which is like your control station. And then the other one connects to a target computer, and it presents itself as a USB device to the target computer. But when the target computer makes USB requests, it doesn't actually handle them locally on the device itself. Instead, it forwards them back to the control host, which then crafts a response in Python software. And then it allows you to create a USB device in Python on your host computer and like rapidly prototype it. And it's really cool. It lets you do some very powerful things like security testing of host operating system, like USB stacks, for example. So it's an extremely powerful tool, especially for security work and reverse engineering. And one of the things that's really cool about it is, I use the word emulate a lot, like we're emulating another device. And I talk about Facedancer like emulating a USB device, but from the perspective of the target computer, it's not an emulation. It's a physical USB device that is connected into it. And it's just that it's implemented through this complicated thing where you're able to just like implement the USB device in Python on the host computer. So later we made GreatFET 1, which was inspired by the original Facedancer. And now, and it has 2 USB ports and can do the same kind of thing. And today, when we talk about Facedancer, we're usually talking about the software project Facedancer, which we maintain, and recently had the Facedancer 3.0 release. And it's really important that we bump the release number to 3.0 because it helps eliminate confusion with things like Facedancer 20 and Facedancer 21, which were the hardware platforms. So once again, we have this confusing situation with like both hardware and software called the same thing. But today, probably when people talk about Facedancer, they're talking about the software, which still has support for the original Facedancer hardware platform, Facedancer 21. It still has support for GrayFET 1 and for Cynthion and other platforms, including there's a new board called Hydra USB made by Benjamin Vernew that's really cool. We have support for that, thanks to their team. And the thing I want to show you about Facedancer is that the capabilities have increased over time. Facedancer 21 was like the latest version of Travis's original board. And it did low speed and full speed USB to the target computer, but it had a bottleneck at 115 kilobits per second, which is 100 times slower than full speed USB. Okay, it's kind of amazing that it's useful as it is at this low speed. But you really can do some very powerful things with it. But it also only has 5 USB endpoints. And a USB endpoint is it's a numbered virtual pipe. It's kind of like a TCP port. And this device controller on Facedancer 21 can only give you 5 unidirectional endpoints. 2 of those are the control endpoint that's mandatory for every USB device. So that really only leaves you with only 3 custom endpoints, 2 in, 1 out. So you really have only 1 bidirectional pipe that you can use, which limits you quite a bit, and it prevents you from emulating certain USB devices. So we tried to improve that with GrayFET 1. We eliminated that 115 kilobit bottleneck, and we have a hardware architecture that can do 12 endpoints instead of 5. And we wanted to build even a yet better Facedancer with Cynthion. We really wanted Cynthion to be the ultimate USB 2.0 Facedancer. And so with Cynthion, you can do high-speed USB Facedancer and to the target computer. And you can have all the endpoints you want. Like the USB 2.0 standard gives you a way to specify 32 endpoints. But like if somebody extends that standard, you could actually do that with Cynthion because the device controller is entirely built on the FPGA and gateware. It's open source gateware. We control it. We can do whatever we want. So I want to show you another demo of like reverse engineering a device by emulating it. Like if you have a USB device and some software on a host that talks to that device and you want to reverse engineer it, probably the best way to start is to like throw a sniffer in the middle and start sniffing packets and see what happens. But what if you have a device but you don't have host software? Well, in that case, you probably would connect it to your device and start writing your own software to talk to it. Your operating system will interrogate it, will enumerate the device and get information about it. And you can look at those device descriptors and have some clues about how to start talking to it. And I would recommend using Python for that. What if you have host software that knows how to talk to a device, but you don't actually physically have the device that you want to reverse engineer? Well, in that case, it can be really helpful to try to emulate that device yourself, like with Facedancer. So let me show you an example. I'll keep this a little on the quick side. If we have, so first of all, I'm going to make sure that my Cynthion is connected, and I'm going to run the Facedancer gateware. So what I'm doing here is I'm actually flashing the Cynthion with different gateware so that I can do Facedancer things. And then I'm going to be able to actually emulate a HackRF, I hope. So if I do, for example, a HackRF info command, you can see, oops, it helps if you spell things correctly. No HackRF boards found. Okay, well, now I'm going to go run a program. I'm going to make a little program. I think I have one at the ready. Oops. HackRF. Oh my goodness. I think I don't know how to type. Typing is helpful. Typing correctly is helpful. Okay, so here's my starter program. There's not much going on here. I have some sort of dummy strings of information to kind of make enumeration make sense. But the big thing I'm starting with, the seed information, is the USB vendor ID and product ID. And these are things that you can look up online usually for any USB device that's common. But that's kind of my starting seed of information here. And so I have a little script that doesn't have really anything except for that vid-pid, the vendor ID and product ID. And if I run this, then it's going to emulate that device. Now I've connected the Cynthion, back to my host computer. So my host computer and my target computer are the same computer right now. And if I run hackrf info now, we actually see found hackrf. And we get that bogus serial number here that I typed in. But then we get a hackrf board ID read, pipe error failure. Well, there's this so now I have to figure out, well, how can my emulated hackrf kind of try to convince hackrf info that we actually have a valid board ID? Well, there's this cool feature in Facedancer called suggest. If I run this script with the -- suggest option and do this again, then I can go back. When I terminate my Facedancer script, it says, why don't you try handling that request with this code? And so I can just copy and paste that into my script. Let me just put that right there. Now, instead of stalling when I get that request, I'm going to reply with something. It says the request was for 1 byte of data, so let's just reply with board ID 1 and see what happens. So we do run this again with suggest. I run hackrf info, and it says, oh, board ID number 1, that's a jawbreaker. Now, jawbreaker was the beta platform that preceded hackrf 1. Oh, so maybe if we want to emulate a hackrf 1, maybe we should try board ID number 2. And I could rename this instead of handle control request 14. I could call it, like handle board ID request or something. So now we run this again, and hackrf info now thinks there's a hackrf 1 connected. But it's failing on the version string read. Well, let's take a look at the version string. Let's see what happens here. What does suggest tell us now? Oh, it says we should handle request number 15, which was for 255 bytes of data. Now, 255 bytes is kind of like the thing you see a lot when a host is just trying to ask for a maximum length string. Like it doesn't really know how long the string is that the device is going to return. Maybe we need to return 255 bytes to fool it, but I bet we can return less than that. So if we were to just return, reply with, so I just pasted in what suggest told me, and then I'll just put ShmooCon version, and I think this has to be, oops. This has to be bytes, not a Python string. And then we'll run it again and see what happens. There we go. The firmware version is ShmooCon version. It totally worked. It fooled hackrf info. Now, there's still more to do to get hackrf info to be fully satisfied, but I'm going to cut my demo short here. There's actually more in a tutorial in the Cynthion documentation that we do this exact same demo, but go a little further. So there's another blog post, actually, written by Mike Walters, which shows you this exact method used. He did it. He used this method to reverse engineer the electronic cal kit for his vector network analyzer. He has this VNA that he got off of eBay, and he doesn't have the thousands of dollars cal kit, but he wanted to kind of build his own. So he used this technique to just kind of reverse engineer this hardware that it doesn't even have with a host computer, which is a piece of test equipment that he doesn't have access to modify or do anything in the operating system. He just connected a Cynthion and started doing Facedancer things. There's another really cool thing I want to, if you want more demos, Martin is doing this video series on reverse engineering the PlayStation 5 controller, which is really cool. He has the first video up, and more videos are coming soon. Now, USB proxy was a capability that was demonstrated here in 2014 by Dominic Spill on the BeagleBone Black. But then later, Kate and Dominic built that USB proxy function into Facedancer, and now it's a thing that you can do on any of those Facedancer platforms that I mentioned earlier. So if we have time, I'm going to tell you really quickly some ways to build USB devices. 3 ways to build USB devices in software. One of them is really obvious, Facedancer, we've already looked at that. Another one is you can build a USB device in Gateware. And Antoine is working on a series of tutorials that are really cool that are going to be part of the Cynthion documentation any day now. And another thing you can do is actually build SoC firmware. So a third way you can build a USB device in software is actually, we have a SoC, a system on chip, which is a CPU built-in gateware that we put on our FPGA. And this is actually how we have implemented Facedancer. So when you run Facedancer with Cynthion, the Facedancer software on your host computer is actually communicating with this back end, which is actually Rust firmware that runs on a soft CPU that is built in that is put on the FPGA on the Cynthion. So you can actually write your own firmware for that SoC if you want. And we have examples of, Hello World in both C and Rust. So 3 different ways to just like create a USB device in software. But if you create a USB device in software, you might also want to have some hardware. Like, does your USB device do anything other than just talk to a host computer? It might need to do other external things. So like 3 ways to build a USB device in hardware. One way is to add something on to the Cynthion. And so we have these external PMOD connectors that are just pin connectors on Cynthion. You can plug things into those. And there's this standard that Digilent has made called PMOD. And you can buy these external PMOD boards from Digilent, or the ones I have on screen here are from 1-Bit Squared, and they're open source hardware. If you're the kind of person who thinks that SSD stands for 7-segment display, then PMODs may be for you. There's also, on Cynthion, in addition to those PMOD headers down at the bottom, just above that there's a row of LEDs, and just above that there's a mezzanine connector. That mezzanine connector is another expansion port, and you can build boards that connect to that. An example of this is Amalthea, which is an experimental software-defined radio platform that we've made, and it's just a little add-on board that plugs into Cynthion. So the USB connectivity is provided by Cynthion, and then just the radio is on that little add-on board. A second way you can build a USB device in hardware is to modify the Cynthion design. Cynthion, of course, is open source. It's published under permission license, a permissive license. And an example of this is the URTI mainboard. URTI is our project to build a universal radio test instrument. And if you look at the top part of this board, it's basically just a Cynthion with some extra bits ripped out. And then we've added a radio to it. Kind of similar to the Amalthea architecture, except we've gone further in actually modifying the original Cynthion design instead of just adding something on to Cynthion. And then a third way that you can build a USB device in hardware is by using any FPGA. Like maybe you have a Glasgow, or you have some FPGA development board, or you've built your own board, designed your own board with an FPGA on it. As long as it's an FPGA that can be targeted by Amaranth HDL, and there are a lot of those, then you can use Luna to build a USB device on your platform. And the only thing you need to figure out is how are you going to physically connect to like a USB cable or connector. And there are a couple of different options. One way is to just use any 2 3.3 volt I/O pins on your FPGA and a resistor. And just that simple connection with the Luna gateware library allows you to build a low-speed or a full-speed USB device. If you want to do high-speed, I recommend using an external PHY chip, like a ULPI. That's what we do with Cynthion. A full-speed transceiver is that block in the upper right. A low-speed is the block in the lower right. They're the same thing. They're just 2 I/O pins, D+ and D-, and a pull-up on one or the other to indicate that, and it's a particular value pull-up, so that the host can detect your device and detect what speed it is. Now, instead of that little block in the upper right, if you want to upgrade your device from full speed to high speed, your transceiver has to look something like this. And it's a lot more complicated. And in theory, you could roll your own PHY, but I don't recommend it. Although if you do, please tell me. I want to see it. It'd be really cool. But I would recommend that you just use like a $1 ULPI chip, which is what we do on Cynthion. So in the future, one of the things that we actually have working already is Luna SuperSpeed. You can actually do SuperSpeed USB with Luna, not with Cynthion. This is a good example of why we have two different names for these things now. Because Cynthion is strictly a USB 2.0 device, but Luna itself actually has SuperSpeed functionality, and we have the capability to use the SuperSpeed transceiver that we used on Daisho, or we have the capability, which is very experimental, to use a high-speed serial transceiver that's built into various FPGAs to do that SuperSpeed communication, which is really cool. But it needs a lot more verification before we can actually kind of deploy it safely. And then another thing that would be cool would be to do Facedancer in Gateware. Instead of having Facedancer in a SoC, it would give us some more capabilities and some higher performance Facedancer things we could do. And another thing that would be really cool would be to do Luna host devices instead of, or USB host controllers in Luna instead of just doing USB device controllers in Luna. And we actually have some work in that direction that's coming from Sebastian, who's created this Teliqua project I mentioned earlier. So he's doing some really exciting things there with Luna host mode. And I want to say thank you to way too many people. The entire team at Great Scott Gadgets has just been phenomenal. They've just put so much effort into all of these projects and more. I mean, I've only told you about the main ones. I haven't even really mentioned a lot of the side projects that support these things. Also, thank you to former Great Scott Gadgets people, especially Kate Temkin, who started the Luna and Cynthion projects. I want to thank various other neighbors in the community who have contributed in various ways, especially, I mean, like, I barely even scratching the surface of folks who have helped create this wonderful ecosystem of open source FPGA tools. Back in the Daisho days, we didn't have that. And that was one of the reasons we were frustrated with the Daisho project and were slow in developing it and didn't see it as a good way forward, was because we were fighting with proprietary FPGA tools. Now, today, we have this wonderful ecosystem of open source FPGA tools. And thank you to the backers of Cynthion on Crowd Supply. I know some of you are here today. Thank you so much. You helped keep us at Great Scott Gadgets afloat during the global chip shortage. Thank you, ShmooCon, for putting on this wonderful event all these years and having me so many times here. And for requiring masks. I really, really appreciate the concern for the health and safety of this community. I thank you all for coming with masks, and thank you all.